Okay, so let's go back and, well, not go back. Let's talk about Unit 5. We only have this and 2 more. Again, this is about 12%. There is a lot of individual topics here. And again, I posted this to Teams under Files, so you should be able to access the PowerPoint in itself. I've also asked you to start making one-page wonders, and I'll probably make another video about that. So, reaction rates. You should be able to do reaction rates. We've done this both as honors chemistry and in AP. You should be able to tell me whether it's the order of the reaction. You should understand that reaction rates are the disappearance of a reactant or the change in concentration of a product. We typically focus on reactants because it's higher concentration, easier to manage. A rate law expression, you should be able to write out a rate law expression given data. You typically will not be given one rate experiment over time. You will be given 2 to 3 experiments with differing concentrations. You should be able to then do a number of calculations based on that. So as the concentration changes over time, you should be able to tell if it's zero order, first order, or second order. You should be able to then write that equation out. If you're given anything that is radioactive, the rate expression will be first order. Kinetics will be the half-life will be 1/2. Time 1/2 is equal to the natural log of 2, which is 0.693 divided by the rate constant K. Elementary reactions. This is when we give you a series of reactions that overall add up to the rate expression, or the overall, the overall order of the reaction gives you the reaction. However, we look at the slow step to determine when we would stop in those, and we stop at the reactants of the slow step. Anything that cancels out is not appearing in the rate expression, and you should be able to write the rate expression from the elementary reaction steps. Based on collision theory, you should be able to tell the molecularity of a reaction. If we have two things combining in one step, then it would be bimolecular. If one thing breaks into two pieces, and that's our slow step, then that would be unimolecular. And so you should know molecularities of expressions based on what the reaction's doing. Boltzmann distribution curve shows basically that it is a distribution of particles, and the maximum point or the highest point is the medium. Pretty straightforward. Reaction energy profile. I've drawn a number of these for you this year and last year. You should be able to see where the reactants start versus where the products finish. And the difference, products minus reactants, will give you whether that reaction, if delta H is positive or negative. If the reactants are higher in energy than the products, then it would be exothermic. If the reactants are lower in energy and the products are higher in energy, then it would be endothermic. You should be able to identify where the activation energy is, where the activated complex is. The Arrhenius equation would give you the dependence of the rate on and relate that to activation energy. However, calculations using the Arrhenius equation will not be tested on the exam. Hallelujah. Introduction to rate mechanisms. You should be able to say whether or not that rate mechanism is consistent with the rate expression or not. You will, so basically you would add up, like I said before, to the point of the slow step reactants, and that should, when added up, and the reactants and products that are the same are canceled, should give you the rate expression. A rate mechanism cannot ever be proven, but it can be supported or rejected based on the rate expression. So, rate mechanism and rate law. Identify the rate law for the reaction from a mechanism. So if you're given a mechanism, say this is the believed to be mechanism, you should be able to determine what the rate expression should be. Or if you're given the rate expression, you should be able to eliminate mechanisms that do not support that. No data collection on this, which is nice. Steady state approximation. This is something I don't typically talk about. I don't see it as a very large portion of the AP exam as far as I can tell. But you can read what it says there. Multi-step reaction energy profile. If there's more than one step, you would expect to see activated complexes for each step. And the rate determining step would have the highest peak or the highest activation energy. So if you had 3 steps, you would have 3 peaks. And if the second step was the rate determining, then the middle peak would be the highest. That's kind of the idea behind this. You should be able to identify whether or not that rate expression and the energy profile are matching. Catalysis. Catalysts are, you should be able to explain what a catalyst is and what it does. Certain things to be aware of, that catalysts are not consumed in a reaction. They are used and then regenerated at the end. It can be consumed, but then it has to be regenerated at the end of the expression, or it is not a catalyst, it would be a reactant. There are different mechanisms for how catalysis works. My feeling that this is going to be a fairly small portion of the exam, only because there's so much else to cover. I would review it quickly, but I would not. The major things I would expect you to see is whether something is a reactant, if something is a product, if it's an intermediate, and then if it's a catalyst. Those are the sorts of things you should be able to identify. So I'm going to stop here and we will start on thermo next one. Thanks for listening.